Hello and welcome to another developer toolkit. So this time around, we're going to be making an area that I really enjoy making these kinds of systems. So this is going to be a set of sensors for our AI characters. Because one of the key things we often need for our characters is an ability to have an awareness of what's going on in the world around them. So typical sensors that we'll often see in games is we'll see vision sensors. We'll often have hearing sensors. And quite often also then a really close proximity or a contact sensor. In particular, if we're dealing with a stealth game, it's quite common to see that as just a final thing so the player can't just stand right behind an AI character for an extended period of time. And depending on your game, you might have other types of sensors as well, but this will give a bit of a basis for it. And one of the key things with this is it's not just detecting that something's there, it's then providing that in a way that we can key off our AI behaviors. And there's quite a big difference between the information we get from the sensors. So if something appears, if we can see something, we immediately have a bunch of information about it. We know where it is, we know what it is, and even if it's just on the edge of our vision, it starts to draw our attention really rapidly. Whereas if we hear something, we know the broad direction, but more than that, we don't necessarily know. But if we continue to hear a sound, then we'll react to it. So we're trying to have that capability within our AI as well, where it's got a bit of variation in terms of how it's actually reacting to this information. But the first step is going to be building up that information. Then we'll look at how we assemble that into something coherent. So let's dive right on in. So you'll see what I've set up here is I have my enemy character here, which they have a vision cone, which I can change the angle of that. And we've just got a visualization for that using handles. We've also got our hearing range shown as well. This just makes it really easy for us knowing where we're at in the editor and sort of what stuff we're able to see. So I actually move the game view down here because that way then that will make it really easy, especially if we go into top-down view like this, for being able to tell where the player is with respect to these. So what we want to do is get the different sort of sensors up and running for this enemy AI. So for the sensors, what I'm going to do, and I'm going to actually set this up in a separate script. The idea being that it's something that's a little bit more modular that you can then add into your own projects much more readily. So let's get our folder set up for sensors. And what I'm going to do is I'm going to actually set up the sensors so that we've got a single script for things like vision, a single script for things like hearing, and then they just feed through to an actual thing that combines them. So we're going to have a sensor processor. Actually, let's call it the... trying to think of a good name for it. Let's set up our vision sensor first, and then we'll work out a good name for that one that collates the information. Because it's going to be on every single character, so it's something where we want to have a logical name for it. So vision sensor. Now, default process that we might go for this is just to be doing a Raycast. But Raycasts are expensive. So there's a couple of things we want to do to actually simplify the process there for the Raycasts and to make it that we're able to be doing that a little bit more efficiently. So what I want to do is, firstly, I want to actually set up a layer mask so that we can opt in or out particular things from that actual sensing process. So detection mask. And initially, I will set this to be detecting everything. So we'll default to everything as what's detected. And I also want to, I set these up in my enemy AI, but I'm actually going to bring these over to the other setup. Or the sensor actually needs to talk to the enemy AI anyway, so it can require a component for the enemy AI. So it's going to have the detection mask. We've already got that angle and the range, so that will help for me being able to filter things out. Because we will need to do a raycast, but we want the raycast to be kind of the last resort, that it's the last thing we actually do, just to confirm. So we want to filter out a lot of stuff without having to do the raycast. So that means we will be able to have our enemy AI, and that will be able to be something we can retrieve early on. Get the component. All right, so in update, what we want to do is we probably want to have something where a common process for this is we actually have a registry of things that are being able to be sort of found. Because we could do like a find object of type, but that's not great. We could just do a raycast based on where we're looking, but that only gets stuff in a single line. We want stuff in a range. So what we want to have is we want to actually have a system where we can register our targets or register potentially visible targets. So we want to have a visible detectable target manager. And we'll give another script for detectable targets. The idea being what we'll do is on things like the player or anything else that we want to be able to react to, we'll give them this detectable target script. It just means as things get added and destroyed, they are able to just register and deregister, and that's just going to make it a lot more efficient for working with it. So we'll do our usual setup for making this a singleton. So we only allow it to be set internally. And then in awake, what we want to do here is, first thing we want to do is check just in case we already have an instance. So if we do, well, we don't want to create another one. So we're going to destroy ourselves and early out, but we're also going to log out an error because this is a scenario that if this has happened, something has gone wrong. So multiple found destroying, just so we know which one we're destroying, so we can track down the problem. That's really what the goal is here, is just making it so that we can easily know that we've only got one of this, and if we do end up somehow having multiple, we can easily detect that what particular one's causing the problem, and also by doing the destroy, we still enforce the behavior we're going for where there is only one of them. So that's an important thing with that. So we're just going to have a register as a detectable target. And we'll also have a deregister. Like that. And then that list of targets we want to have easily accessible. So we'll have a list of detectable targets, all targets. And again, only private settable. Get that nicely initialized. So these become quite a straightforward thing of we add target and then we remove. So that's good, can do that. And then in our detectable target, we'll on start a register, and then on destroy, we deregister. And because the detectable target manager could already be destroyed, because we're not necessarily able to control the destroy order when we unload a level, so we want to just make sure it's valid first. Cool. So now we've got things that can register and deregister, so the vision sensor. Now we can do our pass here, because we can grab all of those detectable targets and check them. So, index. Now the reason I'm using a for loop that uses integers rather than a for each is this is going to be running a lot. It's running every frame, it's running on every AI every frame, which means the performance of it, we want to try and actually make this as efficient as possible. And for each does have more overhead than using a just integer-based for loop. So that's why I'm going for an integer-based for loop in this case. So index is less than detectable target manager, targets, and we can just get the count of that. So then we have candidate target. We just want to retrieve it out so our lines of code don't get too messy. So, okay, we're going to check every candidate target. Check all candidates. So first thing we want to do is, because we might also be a detectable target, so let's eliminate ourselves from the potential list here. So f candidate target game object is equal to this. Continue. Skip if the candidate is ourselves. So that's an important thing. So, okay, what we're wanting to do here is the Raycast is actually going to be the very last thing we do, because it's the slow thing. So right at the end is the Raycast. Before that, there's a couple of other early outs that we can do to filter this. So one of the things would be checking the distance. The other is, well, we know we have a vision cone. We only want to see things within that. So that is actually something that the check for that is really, really cheap. We can check it using something called the dot product. And we'll see how that works, but it gives us a really cheap way of being able to do that check of, is something within that vision cone? So something has to pass all three of these checks before it actually does the Raycast. So it's going to keep it significantly more efficient for us. So, okay, let's firstly get our vector to the target. Vector to target. So to get the vector to the target, it's the candidate target's position minus our position. So that immediately is something where we can check the distance. So what we can do is, okay, f out of range, cannot see. So we could then say, well, f vector to target and its magnitude, if that is greater than our linked AI's vision cone range, then we continue. And this, we could actually make this a little bit more efficient. And this is a very, very micro optimization. And depending upon how magnitude works within vector 3, if vector 3 has already calculated the magnitude, this micro optimization won't actually give us any saving. If it hasn't already calculated it, then this would give us a saving. So what we could do is we could check the square magnitude against the square of the vision cone range. That will just give us a slight optimization in that we don't need to do a square root, which is a slower operation. We are doing an additional multiplication here, but that's not going to cost as much as the square root would. And what we often do, in particular in larger projects, is we would cache things like the square of the vision cone range. So, okay, we've done the early reject for distance. Now we check if we're outside of the vision cone. So if we're outside of the vision cone, cannot see. Now the vision cone is defined by an angle, And in particular, if we go and take a look at it, the vision cone, we set it to, the moment it's set to about 70, 80 degrees. And so that's defining not the entire angle of it, so not the angle from the far left to the far right, but it's half of the angle. And that's actually something that we can make use of. Because if we took the cosine of where something is in this, if something is directly forward, the cosine of that angle to that character is going to be 1. If we were directly perpendicular, so directly on our right or on our left, the cosine of that angle would be 0. So cosine from far left to far right goes from 0 up to 1, back down to 0. And then on the other side of that, behind us, it then goes from those 0 points to -1. So if we take the cosine of our vision cone's angle, we can check that against the cosine of the angle to our target. Now, cosine is not necessarily the cheapest thing to calculate, but we actually don't need to calculate the cosine of the angle to the target because the dot product of the vector forward with the vector to the target is equal to the cosine of the angle when we normalize those vectors. So that's a property that we can use to allow us to do this check really cheaply. So what we would say is f vector 3 dot of vector 2 target normalized with our linked AIs transform forward. And I'll actually change this to linked AI. Technically it'll be the same, but just to keep it consistent. So f the dot product of this is greater than mathf cosine. Now it wants the angle in radians. So what we would often do in a case like of this is we would cache that. So I would have something here where we have an awake, and I would set up something like cos vision cone angle, private set it to something invalid, or something that'll definitely not be correct to begin with. And then we do cos of vision cone angle. It's mathf cos vision cone angle, which is in degrees, and we convert that to radians. So this is a common thing that for the user-facing stuff, so for us in customizing in the editor, we would actually specify it in degrees. That's a bit more of an intuitive measure for us. And then internally, we just cache it as a cosine version of it. We could even be doing a custom inspector that actually does that translation for us. So in this case, we can just go and check with linked AI cos of the vision cone angle. So if it's greater than it, then it means we can see it. So we check. If it is less than it, then it means we can't. So the dot product is super handy for checking if something is within an angle range. We can also use that for checking if something in front of or behind us. So now what we've done is we've filtered out things that are ourselves, so we're not checking against us, filtered out things that are too far away, and we have filtered out things that are not within that vision cone angle, which means now we can do the Raycast. So we store the result, hit result, so f, we do our Raycast, and so our origin point is going to be our linked AIs transform position. Now this is something where we could, with our linked AI, I might set up here a thing that what we'll do for now is eye location. And that can just for now map to our transform.position, because this way we could then customize that. We're also going to have an eye direction. These won't be different for the moment, but this allows us for, if we were wanting to, we could easily go and change that later. So this just means eye location, and eye direction. Oops, that stays as that, but then this changes to eye direction. So we're doing a raycast from our eye location. Now the direction, we have our linked AI eye direction. Now we want a version where we get the raycast hit back out. So we have our out hit result. Now distance, we have that, because our linked AI has our range. And we have our detection mask. Now, this one for controlling whether we hit triggers. This is something where if something is a detectable target, we want to hit on it regardless. So I'm going to set that to collide. Just because if something is we're already doing filtering that this has to be something that is a registered detectable target, so there's no reason to filter it out even further. So now we know we have seen this. So linked AI, and what we can do, report can see, and then we would go hit result. Actually, we don't even need to do the hit result. We can just pass it the candidate target. So we can see it. And because it's something that we can see, that means we just pass through that direct info. So our enemy AI here, what it's going to do is we're going to have a public void report can see, detectable target, seen. And all I'm going to do initially is debug log and see name object.name. So just log out saying that we can actually see this particular one. So let's link some of this stuff up. We obviously need to give our AI its vision sensor. Now detection mask, I'm happy for it picking up on everything at the moment. Actually, no, I'll turn off Raycast Water UI. So we'll just pick up the default layer. Make sure our character is properly in that layer, which it is. So our player, we're going to give the player the detectable target script. And in managers, just going to set up our detectable target manager. And we'll bring this in. So that's good. So what we were hoping to see is that we start seeing messages saying that we can be seen once we are over here in the vision cone. So we can see we had the can see message appear. And what I'm going to do is I'm just going to bring the console over here so we can see it side by side. And I'll select the enemy character so we can see the vision cone there. So I'm here in the vision cone. As soon as I move out over here, wow, so this, it's still saying that it can see us. And that is because the raycast was just checking that it could hit something, didn't check what it hit. So we need to check hit result, and we can get the collider. So we can't just directly go to the game object, but we can get the collider game object that is equal to the candidate target's game object. Then it can see it. So final little bit of a check that we need to be doing there, just to confirm that yes, we're actually seeing the correct target. So if we run this again, what we should see is, okay, can't see us. let's skirt along the wall here. So I'm in the vision cone, but blocked by the wall. Now I'm here, and it's managing to not see me. So likely what we need to do is we may need to do a hit result collider get component in parent, because we are potentially hitting on a child of the object. So our collision's hitting that. So we need to actually go and retrieve the parent one. So if that is equal to our candidate target, then we report that we can see it. It's a common thing you'll run into where we do this sort of separation where colliders, things like that, might not necessarily be on the particular object that has the script on it. So it can just be a handy way of being able to work with that. So we're still getting it that it's not saying it can see us. Now, the other thing that we have missed here is this. We don't actually want to do a raycast in the direction we're looking. We've already established this is within our vision cone. So what we actually want to do is look along the direction to the target. That's where we want to actually be looking at this stage. So if we wanted to make that a little bit more efficient, what we could do is vector2 target normalize, because that way then we're already using the normalized value here. So that just saves on having to recalculate it again. So if we run with this, what we should see is we'll be able to move along the wall here. And we can see we're moving along the wall. It's not registering that it can see us, not registering. As soon as we're here, it can see us. And as soon as we go out of the vision cone, it can't. So we've got our vision sensor going. So that's good. Vision's up and running. Well, okay, vision's going. Let's get our hearing sensor going as well. So we've got vision sensor, hearing sensor is going to be the next one. And while we're at it, let's also set up the script for our contact or proximity sensor. Proximity sensor. Cool. So hearing, what we want to do there is, again, similar to with the detectable targets. Our AIs are typically we're not going to have them link into our actual audio engine or things like that. We could, but what we'll often do is we'll kind of cheat, and we'll have things like so we would have so essentially a sound manager, but it's tracking things that have actually been emitted so that other AIs can react to it. So what we would have is something like our reactable sound manager. That's not the greatest of names for it. I don't want to call it a sound manager because that might be something that's actually managing the playing of sound. So I might actually call this the hearing manager. And we'll have that set up here as well. So the idea will be things that emit a sound can tell it, and then it can tell other things. Hearing manager. So we can link that up. Now, hearing manager is going to work quite similarly to the detectable target one. And I am just going to nick all of this code because we are largely going to be using the same code. It's just going to be a little bit of repurposing. So what we want to be able to do is hearing sensor. And sensors, because what we will register is we register the things that can listen to sounds. So hearing sensor. So the idea being is the AI will say, hey, I'm a thing that cares about sound. Tell me when a sound has been played. So all sensors, and then our hearing sensor is going to actually register with that. So it will go hearing manager, instance register, we register ourselves, and then it's going to have something where it will be able to say on heard sound, and it will have we'll give it a location. So it will have heard a sound, and we also might want to have a category to that. So I'm going to have a category here, heard sound category. So I can react to a couple of different things. So this is going to pick up category, and we might also have an intensity, I think would be appropriate for this as well. Because if we think about sound, the information we typically get from sound. So with vision, it's a case of, oh, there I've seen this thing over here. Whereas sound, especially if it's an unfamiliar sound, it's a case of, well, I heard something from that direction and it was loud or it was quiet. And so we get a rough sense of proximity and size of something based upon that intensity. And that's something we kind of build up over time as we experience different sounds. So the hearing manager will have an interface here of hardware void on emit sound, or on sound emitted, and that will have a location, it will have a category, and it will have an intensity. Then all this does is this notifies all of those sensors. So for each sensor in all. Now, because this is not running a heap, I think a for each is going to be minimal impact for this. On heard sound, location, category, intensity. So that's good. That will just notify all of the sensors. And similar to what we did with the detectable targets, when we get destroyed, then if we have a hearing manager, then we deregister. So that's good. So the hearing manager serves as the central sort of routing point for there being sounds, which the sensor is also going to require the enemy AI, and it will also store that. So we're going that to be detected, but we would have our enemy AI, linked AI. We will register or keep track of that. So we've retrieved that. Because what we can then do is when we heard a sound, we need to check that it's in range. That's really our only criteria with the sound sensor of checking that range. So, okay, well, if vector 3 distance between location and our linked AI, now we could have a hearing position, stuff like if that, but in this case, the eye location I think will be close enough. We'd probably end up using that as something like head location, most likely. So if that distance is greater than hearing range, then we do nothing. Outside of hearing range. And then otherwise, well, we tell the linked AI, report can hear. So we say that we heard something at a location. So you'll notice with hearing, we specifically are not providing the particular thing that has actually emitted this. So we've got the category and the intensity. And then we will bring this over to our enemy AI so that we can report that. Word, sound, and we can put in the category at the location with intensity of intensity. Now I might actually pass through the source target for this potentially, so I could do that. I'm at the moment going to intentionally not, just so that we are not sort of providing too much info. What can here? So now we need to emit some sounds. So the character motor, if we go over to that, then I already have stuff for playing sounds. So we already have, I look for sound. So we have our footstep audio. So what I would do is a hearing manager. And I would say on sound emitted. So I can give the position. This was a footstep, and footsteps, okay, what we could do is we could check if we're running. So if we're running, maybe that's a intensity of 0.2. Otherwise, it's an intensity of 0.1. We could also have one for when we land. So we've got our on play land audio here. So we could say this, maybe when we land, that has a slightly higher sound intensity. So what we should see with hooking up then our sound sensor is that our enemy can react to the player moving. So hearing sensor, we bring that in. So we've got our hearing manager, we've got our hearing sensor. Let's run this. And what we're looking for is seeing output indicating that it's heard us as we move around. So we're not probably in range yet. Now we're in range, it can see us. Here, it can hear us. If I sprint, it's at a higher volume. And we can see the sound ones jump. So it's activating, but at a larger range. So that's good. So we've got vision, we've got sound. We just need proximity then. So proximity is going to be able to use a similar process to the other ones that we've got. So we've our proximity one, well, I'm keeping everything configured on the enemy AI. So I would have public float, and we'll set up a serialized field one here. Proximity detection range. We might make that really quite short, so a fairly close range. So then we have proximity detection range. Just makes it easy for us being able to access it. And what I'm going to do is we can already see I've got a bunch of debug ones here. So I'm going to also set up another one for this. Proximity, range color, new color, and we might make that one, let's make that one white. Should mean that it stands out nicely against the other options. That's color. This will just allow us to come down here and we can then draw our detection range. So we draw the detection range. Maybe detection color, we just look up that. So it's just going to make it so we can easily see it in the editor. And that's a really important thing there, that it just makes our life a lot easier if we can easily, when we're placing a character or as we're doing just for testing purposes, be able to look at the character and then click on it and see, okay, here's all of the ranges. That would be something where it'd be handy to also potentially draw those in game, but this will work for what we're doing. Let's give it a proximity sensor. Now the proximity sensor is going to need a lot of stuff from the detectable targets, so it's going to do a fairly straightforward process of index. So again, it's running continually, so we want to keep it as efficient as possible. Index is less than our detectable target manager. And remove the index. So all we need to do for this is check our distance. So the distance between. So in this case, we also need the setup for our linked AI. So we have that same process. Enemy AI, linked AI. And we'll just retrieve it. So we just want to check the distance between linked AI, location, and the detectable target manager. So in this case, again, I want to pull this out into a separate variable. And the target is equal to detectable target manager instance, all targets, index. And again, skip if it's us, skip if ourselves, because it could be candidate target game object is equal to this. Because especially if you have something where AIs are able to attack AIs, this is a scenario that could and would occur. So we check our location with the candidate target's position. So if that distance is less than or equal to proximity detection range, then linked AI report is in report in proximity. And again, in this case, we just pass in the direct target. Because what we're doing is saying in that close range, we have full information. That's the idea there with that. So we then have technical target, and sense. That'll just mean if we get too close, as well as hearing us, it will also be able to just directly sense us. But what it does with that information is then what we'll see in the next stage, because we've got all these sensors, we've got all this information, then we want to combine it. We want to synthesize that to allow us to make decisions. So you can see, and I'll just bring up, make sure we've got our console visible. And make sure we've got our AI selected so we can see when we're in that range. So we're up and running, can hear us. It's not going to be able to see us, but I get too close and then it can sense us immediately. So good, we've got all of our different sensors up and running. You can bring this up so it's in the main view now. So we have all of our sensors and we've got all this information. But now we need to synthesize it. We need to combine this into something where we actually have a bit of a tracking for stuff. So what I'm going to do is I'm going to actually put this into a separate class. So awareness system. Because we want to be able to distinguish between something that we can hear, something that we can see. We want to be able to have stepping stones with that information. And if we think about what we would do, and this is always a good approach, I think, with AIs, think about what you would do. So first thing is, if I hear something, I might ignore it, but if I kept hearing a sound, I would look towards it. Similarly, if I see something moving on my peripherals, I might not react to it, but if I see it there for long enough, I would probably turn and look at it. So the speed of something being detected is going to depend upon what information we've got coming in. Proximity is going to build up, we want that to build up really rapidly. Hearing, we want it to build up slowly. And vision, again, slowly, but based upon where it is in the peripherals. That's how we want to sort of work this. So key thing I want to have is I need to store a bunch of information. So I'm going to have a class, tracked target. So with that tracked target, well, it may have a detectable target. So it may have that. It also is likely going to have a position. So that would be a raw position, because what I would likely have here is some further stuff in terms of detecting that. And then we want to have public float last ticked time, or last sensed time. The idea being that as we have been out of something's reaction, it stops reacting to us. So we want things to be able to disappear. So last sense time. And then we want to have something that's keeping track of how aware we are of it. And with this, 0 equals not aware, which will be cold. 1, so then the 0 to 1 range gives us a rough idea. So no set location. And then 1 to 2, likely target, and we have a location. And I'm going to put these all down here so you can see them next to each other. So these are just the ranges we want to be adopting for this. 1 to 2 means that it's a likely target. And then 2, fully detected. So not aware, anything that gets to that stage will get culled. 0 to 1, so things that we hear, hearing will push stuff in that range until it gets to 1. Whereas vision will start something immediately in this stage. The proximity one will also start things in at 0 and build things up. So different things will contribute in different ways. So, okay, that's our setup there. So then what we want to maintain, tracked targets. So this is just going to keep our list of all of these different ones. And so our enemy AI is going to feed information through into these. So our enemy AI will be the one that has the awareness system. So it will require a component of the awareness system, and it will just retrieve that. And we're just going to store that. So the idea will be is the awareness system will be able to tell us, hey, this thing's happened. And it will be the thing that comes back and tells us, yes, you have detected a thing. So it just gets the information fed directly to it. And exactly the same as it's coming in. So report, and here, allocation, category, intensity. So with things like this, there is a lot of sort of piping through of information. And I recognize that it does seem like, oh, why am I doing this? I could just all integrate it into the one thing. The idea is that this means I can give something the ability, different sensors, just by attaching a component. It's taking advantage of that modular architecture that we have available to us. So it just means that it's a nicer way of working with things. So I'm just going to bring these functions over to the awareness system, but initially they will do nothing. So, okay, that's all being piped through. Now hearing, we generally do a little bit of a cheat with the hearing side of things, where what we actually would do is we do provide a game object for it. And the reason being is that we provide it, but we don't give the rest of the AI access to it. So the sensor system has a little bit more information, but it doesn't tell the rest of the character all of that information. So we will actually pass through that source, the game object. Just pass this through for all of these. The linked AI will also need that as well. It's just going to make it possible for us to transition something from being a thing that we can see to a thing that we can hear. Sorry, a thing that we can hear to a thing that we can see. So we pass this over. And we don't need to do anything more with the vision sensor, but this, when we emit a sound, we'll pass over the game object. So as I said, although we have this extra information that we are providing through, we don't tell the AI that information. So it doesn't tell its brain, it gets the info, but it doesn't actually do anything with it. So, okay, we've seen something. Well, we want to have this model that the further away, the more out of range it is, the less sort of we're seeing it. So our awareness system, what we would often have is animation curve, and we can rig up here, so vision sensitivity. So what we can do is, if you remember, the dot product goes from 1 in the center, so directly ahead of us, to 0 at the edges. So what that means is if we set up on the AI character, we can control essentially that speed of detection. So our awareness system, we bring this in, and if we take a look at what we want for the curve here, we can start off with our default S-curve. Can add in a key, that this key, its value is going to be 1 at 0.5, and then the value there is going to be 0, and then we can just flatten this. So what this will mean is this is going to be how quickly things get detected. So in the center, directly in front of us, we will detect things really rapidly, whereas on our peripherals, we'll detect them really slowly. So this is an important thing. As this information comes in, we then do a bit of extra things with it. So our enemy AI is passing through the info. Now our vision sensor, if you remember, we already had some stuff here for getting our vector to the target and for getting the dot product. So we're going to use a similar thing here. So what we can do is firstly our vector to target. So that's our scene targets, position, minus, and again, this is going to have our AI. So I like doing this approach where we do a require component and then we retrieve stuff in the code. The reason being is that it's very hard to then forget to link things up. Just makes it a lot easier to make sure you've got things connected. So linked AI, location. So we take that and I'm going to normalize it. So we've got our vector to the target. So then we can get our dot product. So our dot product, that's going to be the vector to the target. dotted with our linked AI's I direction. So we have now the dot product to target. So that's going to be 1 in the center, 0 in the outsides. So then we can take our vision sensitivity and we evaluate it at that dot product value. So that's giving us a further bit of information there in terms of factoring in that sensitivity. So what we also want to have then is just, I think, a general scale on this. So that's our vision sensitivity. We also want to vision base awareness. Actually, I'll make that minimum awareness. And we want to have the rate that builds up at. So vision awareness build rate. So this is how quickly something will be detected. So if something's right in front of us, how rapidly do we want it to be detected? So this is going to be per second. So we've got to go from, our minimum is going to be 1. We have to go from 1 to 2. So it's how quickly we want that to happen. So essentially, our reaction time. So if I made this something like 10, then that would mean the AI would react in 1/10 of a second if we are standing directly in front of it. We probably want it to be faster than that, potentially. I'm going to set it to 1/10 of a second for now, but that will give us a base sort of setup for it. So we multiply this by the vision awareness build rate by time dot delta time. So this is the awareness contribution this frame. So awareness, and then we can add that. So determine where we are in the field of view, or where the target is. We've got where the target is in the field of view. We are determining the awareness contribution. Awareness contribution, so that's how much it will add this frame. And then, so what we would have is update awareness. And it's going to update it for this scene target. So what we'll do is we'll provide in its game object, scene target. We have its position, so we can directly pass that in. And we're also going to pass in a few other things. Vision minimum awareness. Because this update awareness is actually going to do quite a few things. So, game object, target geo, we have our detectable target, have a location. So it's trying to make this a generic thing that will work for regardless of which ones we're dealing with. So position, awareness, and min awareness. Because the first thing I want to do is check if this target is already there. So what I might actually do in terms of structure for this is I was having this as a list. Even better, it's going to be as a dictionary, because that makes it really quick for me to check, is this already registered? Because then I can say, okay, if targets contains key, and I would check if it doesn't have it. Not in awareness registry. Well, not in targets. So then what I would do is I would be able to say, well, target game object is equal to a new track target. Just so I'm storing it. So I know then the remaining code here, I can assume that it already exists. So, okay, it's a couple of different scenarios. This could be the first time we're detecting this. This could be a case where we're updating it. A few different scenarios there. So what we would do is firstly targets, target game object, and let's fix the naming of that. So we have a few different ways of how we could do this. We could push the updating of this into the actual track target thing, or we could be doing it here in this code. It doesn't really necessarily matter too much which one we do this in, but I might push this stuff into that class. Awareness, min awareness, and I might say that its version of it can potentially return true if it's crossed over a boundary. So if it's crossed over a boundary, then we'll do something. So again, that means we can set up the logic here. It's just keeping it all a lot more modular. That's really the goal for this, making it that it's something that we can just very easily plug into any of our sort of setup. Okay, so this has now got to update info. So by default, we'll return false. So our target. So detectable, it's just automatically set to the target. Raw position is set to the position. Our awareness here is going to need a couple of setup. So our awareness, firstly, well, it needs to be the max of awareness plus, well, actually we can do the max of making our awareness and our min awareness. So the idea here is that we're setting a minimum threshold. So this will mean that this will always start at this value, but we need to combine in our addition of the awareness here as well. So what we could do is, well, if we add in that, we could add that in on both sides. That gets a little bit messy. What I would probably do to make this a little bit cleaner is awareness is equal to mathf. Well, we've already clamped it between that, so we could then say our awareness, we just add in. So actually, yes, if we do that, and then we clamp it, because we do have min and max values. So mathf.clamp, and we clamp that between our 0 and 2. So we've updated the awareness. Our last sense time is just equal to time.time. So we'll do the updating of that over here. So we're updating our target, we're updating our position, and we are switching over to this in terms of where, if the awareness has changed, then we update it, we keep it clamped, which is good. Now, detectable, if we hear something, we won't have a detectable target, but then when we see it, we add that target back in. So that's fine. That will update correctly. And what we could do is, I'm going to set that to -1. And what we're looking for is old awareness. So we store our current value. And then we're checking for a couple of things. So if old awareness is less than 2, and awareness is now greater than or equal to 2, then we return true. So that's something where we have gone from it being a likely target to now it is fully detected. We can also check, well, if the old awareness was less than 1 and the awareness is greater than 1, then we also return true. So this is just detecting have we gone above a threshold. And that looks pretty good. Those are our main sort of cases that we want to be reacting to. So that looks pretty solid for that. Update target awareness. So if there was a major threshold change, then we can log information out there. So threshold change for game object name. So that will work on the vision side. What about the hearing side? Well, hearing side, we already have stuff like intensity, things like that. So we can have a similar thing with hearing, where hearing minimum awareness is 0. And it's also going to have a build rate, hearing awareness build rate. And that's going to build a lot slower. So I'm going to set that to 1. So it's going to take it a lot longer to actually build up to reacting to it. Might actually make that even lower. So that would take it quite a chunk of time to react to it. So, okay, well, when we've heard stuff, what we would be doing is, again, update awareness. We have the source, game object. Now, we don't have a detectable target, so that's going to be null. We do have a position, so we have the location. And now the awareness change here, well, the awareness, that is going to be our intensity of what's come in, multiplied by our hearing awareness build rate, multiplied by time.delta time. So quieter sounds will build it up slower as well. So it gives us that hearing minimum awareness. So that looks pretty solid. We could also have stuff with directionality in there as well if we wanted to have the hearing, because our hearing is somewhat directional and different creatures, different characters could have more or less directional hearing. So we can easily bundle that in if we wanted to as well. So, okay, we've got that linked in. Now, one of the things we do want to handle here is, because with that, with hearing, we're passing in a null. So detectable here, we really probably only want to change this if target is not equal to null. So we never lose a detectable target, but we can gain one. That just prevents something when it goes out of sight being sort of stomped over. Because we won't pass through the information unless we have it, or unless we need it anyway. And then proximity is going to be a similar thing where it's going to have a build rate as well. Serialized field, float, proximity, minimum awareness. So it's again going to start at 0, but its build rate will be much higher. So it's going to build pretty rapidly. So a couple of seconds. I think if we actually went for 1, that's going to build it pretty rapidly. And it ends up being an even easier setup here. So the awareness contribution, it's going to be, it's a flat intensity. So it's the proximity awareness build rate by our time.delta time. And we update awareness. So the awareness, well, we know our game object. We know our target. We know the target's position. And then we also have our awareness and our min awareness for proximity. So the end result of this is these will all build up. We update the last updated time, which is good. Then we could have our decay of this. So just want to get the decaying happening as well. So awareness, decay rate. So the idea behind this is going to be how rapidly the AI forgets about something. So we don't want that to be too fast. So if we think our cap is 2, we don't want to go from that to being fully sort of not detected too quickly. So we might drop that to 0.1. because the decay here, what we do, decay awareness, mount. And we would say our awareness minus equals that amount. And what we do is we return less than or equal to 0. Okay, so we need to decay our awareness here. So what we'll set up in the update is just do a for each, and we will loop over all of the particular game objects. So game object, target, game object in targets keys. And then we'll say for that, targets, target name object, decay awareness, and we give it the amount. Now we've got this returning true if that awareness is below threshold. So if that's the case, then we want to store this in a list of ones to clean up. So list of game object to clean up. And what we would do here is to clean up, we add game object in there. Then at the end of this, clean up targets that are no longer detected. So what this would be doing is, okay, well, if it's no longer detected, then we can remove it. So for each target in to cleanup, and then we say targets remove, and we give it the key. So that will get rid of ones that are no longer detected. So, okay, we've got threshold change detection happening here. We probably want a threshold change detection happening here. So I might actually change this around. So this does a similar thing of storing the old awareness. And then we have a similar version of these, where if our old awareness was greater than or equal to 2, and now we're less than that, then we'll activate. If it was previously greater than or equal to 1, and now is less than that, then we also return true. Or if the awareness is less than or equal to 0. Take those. So now this is indicating if there's been a change. So that does also mean here we only add things in if that awareness is actually below 0. So if targets awareness is less than or equal to 0, then we clean it up. Otherwise, we can do a similar message to this where the threshold has changed. And we also have our target game object here. It's a whole bunch of bits that we've hooked up, but this should give us something where we are being able to see that the awareness is changing and that we're getting messages indicating that it's reacting to that. And what I might do is also just then have this, that when it's displaying this information, that it also includes the awareness. Just put in a bit of a space there, and then we do the same here for where we're making this change. So that looks good. So we want to see that if we move around a whole heap, it starts to react to us. And we also want to see, when it sees us, that it reacts a lot quicker. So I'm in its range now. So we saw a threshold change. It went up to 1. And then it went up and hit. So it's sort of bouncing around a bit, and that's because the decay rate, which that would happen. So we may want to have a little bit of a delay there on that, where it doesn't start to decay until it hasn't been seen for a certain amount of time. Serialized field, awareness, decay, delay. We want to delay by a little bit as well there. So that way then we don't start decaying things until it's been a little bit of time before we actually are sort of tracking it. Because then this, it's our decay time. So what we would do is F the last sense time. So if our current time minus that, time dot time minus that, if that is less than decay time, then we just return false and we don't decay anything. Detected too recently, no change. So we have to be out of range for a bit before it actually will properly detect us. So let's try this again. And so what I'm going to do is get in range. So very rapidly sees me. And then what we should see is after a bit of time, it then hits 2. Now it's staying at detected. And if I move out of range, you can see that it detects we've immediately gone out of sight. It'll drop down to below 1 before too long. So this gives us our intervals for sort of being able to search. But then what I could do is if I come here and I bounce around, then we would be hoping to see that it would be detected. But what we might be hitting is it might actually be sound sensitivity needs to contribute more. We're likely not contributing enough. If I stand right behind it, it rapidly detects it. So what we would do is our hearing awareness build rate, we might increase that. So if we double that, because we want it to be able to react to having heard us. So let's try that again. And what I'm looking for is being able to run around here, and that should, what we're after is that ticking up the awareness. And so we're likely seeing a case where, yeah, we still need to ramp up that hearing sensitivity more. So what we can do there is if we go and select our character, then our hearing build rate, we can increase that up again. So we've doubled it again. And it might also be the intensity, because if we think our sounds are coming through, we've got 0.1, so that's a 0.1 contribution, and then we're scaling by delta time. So it's potentially just a really low threshold there. So what we could do is let's crank that up to 10. That should make it react quite rapidly. So these are something where, depending on the character, you do need to do a fair bit of stuff to balance them. And so you can see that still, I would expect them to be reacting a lot quicker. Now the sounds don't get emitted frequently. So we're probably also hitting a bit of a decay aspect there, where it's decaying it really rapidly. So what we could also do is in the character motor, those sound intensities are pretty low. So let's make these sound intensities higher. And so jumping will also make fairly high. Because if we think these aren't emitting continually, they're emitting periodically. So it's always the thing with sounds is you need to balance that. Now we could make it that every time you're moving, rather than just when it plays the footstep sounds. But it's, I think, a good thing to have them be somewhat in sync with each other. So there we go. That kicked off it reacting. So with that, we can probably lower our hearing awareness build rate a bit so that it's, it is now building very, very rapidly. So we can probably bring this back a little bit because we do want it to be detecting us probably at about that point, sort of when we're sort of crossing the room there. So I think that probably a build rate of maybe about 5. Because 10 felt a little too fast. It did detect us a little bit too rapidly. I would say 5 might be a better one. There we go. So it's activating when we're sort of getting close. So, okay, we've got it activating. Now, we just need to have it do the final little bit of telling the AI. On suspicious, so that's when we are suspicious of something. And that is not going to give any extra info. That's just going to be able to say that, yep, it's suspicious. So text. I hear you. On saw target, or on saw target. And this will actually provide targets. This is what I mean about we don't tell the AI all of the information. So I see you. So that will change as we cross above the thresholds. So on suspicious, and actually I'll make that on detected. Then we would have on lost detection. For that again, where are you? And we just put in the name. And then we could also have another one for when we've lost suspicion. Again, we don't have that particular, any extra information there. So we have feedback. Must be nothing. So these could then key off audio cues, they could key off AI behaviors, different things like of that. And so we can then activate these here. So in this case, we know that we're going down. So F that awareness. If that awareness is above 1, then what's happened is we lost detection. Otherwise, what has happened is linked AI, we lost suspicion. So we can get rid of the debug for the threshold change. We also, linked AI, in this case, so lost suspicion is going to, so if we think lost detection is when it's still above 1. So actually we want this to be, if it's greater than or equal to, greater than or equal to 1. So we lost detection, so we see it still, we're seeing it. Whereas this one, it's gone below 1. And whereas in this case, we've lost them entirely. You go. So we would then have fully lost. So this one. So we're just providing different cues so it can be reacting to us. And then we have a similar thing for when we're increasing it. So, okay, well, F targets, target game object, so that awareness is greater than or equal to 2. Well, this one on fully detected, again, we'll output some text. Just so we know what's happening. So this will be the on fully detected. On fully detected. Provided the game object. Then otherwise, we're wanting to check if the awareness is above 1. And in that case, on linked AI, we are now detected. And then the final one is for suspicion. So just give us different thresholds so we can activate different logic there. And what I'm going to do is I'm going to bring the scene view down to here so that I can have us be able to see what the AI's text is. I'll increase the size of that feedback panel there just because we're going to need a bit more space. Probably like that. That should give us enough of an indication. All right. So what we're looking for is, as we move around, so moving around over here should be nothing. Once I start to get closer, we are wanting to see that it can see us. Now we're fully detected. So let's move away. So it can't fully detect us anymore. So it's saying, where are we? And if we watch over time, we should then see this drop. So we're dropping to another awareness state. And then eventually that will go to must be nothing. But if I start moving around, then it immediately becomes suspicious of us. Now we're not quite reacting to, so if we go to this, this doesn't give us a reaction for going from 0 to nothing. So it would check if old awareness is less than or equal to 0 and awareness is greater than or equal to 0, then we return true. So just indicating the threshold change. And what that should now mean is that we get the full range of it. So as soon as it starts noticing me moving or hearing me, I should see it change to, so I'm inside the range, it can hear me. If I wait and let that decay, it'll go back to saying that it must be nothing. As soon as I start moving, immediately is a case it can hear me, but it's not actually going beyond that. Now it can say that it can see me. But again, I disappear. So it very rapidly goes between the different states. So as soon as I disappear behind it, so this would be stuff where we could then be turning towards it. So as soon as something is suspicious, we could start to face the target. So what we've set up here is a bunch of different things. And we've made it nice and modular for the architecture. So there's a couple of overall manager things we set up. So being able to keep track of things that can be detected, being able to keep track of things that can be heard. So we've got those as managers just as an easy way for retrieving things. Then on the Anime AI itself, each sensor is its own standalone script, just so that it can do its specific task. And so it means that a particular character, say I want to remove a sense from it, I can. This character, I could remove everything except for vision and proximity. And so then now I can more readily sneak up on this character. So I can head over here, and then I can get right behind them, and then now it's detecting. So it makes it easy to add in and remove different sensors, and then we have something that combines it. So its job is to maintain that awareness information, and it has more info than the AI does. So information gets passed to it, and then it chooses what it tells the AI back intentionally so that it can have full info, like knowing exactly where a sound is coming from, but it only tells the AI what the AI needs to know. So we can filter that information, and this allows us to set up things like reaction times, stuff like this, how long it's going to search for a character, allows us to key off the behaviors really easily. And by just changing things like our vision sensitivity by minimum, maximum awarenesses and build rates, we can then get the characters behaving in kind of the way that we're after. So different AIs could have different setups here. So dive in, experiment with this. It's nice and modular, so you should be able to add that into your own projects if you want, and see how you go from there. See the kinds of cool things that you can create. So folks, I hope you found the video helpful. If you were looking for the code for the project, then you'll be able to find the link to that in the description below. If you're looking to support the channel, then chucking in a like and subscribe is always a huge help. If you're looking for other ways to support the channel, then I do have a Patreon, and the link for that is in the description below as well. If you've got any questions, just give me a shout. Just chuck in a comment below. Have fun.